Hi guys, today I want to talk about calculations and formulas, and I understand that it probably sounds very boring, but I think there just might be a possibility that you might find some of them interesting. The reason that I've been thinking about these formulas is sometimes I think about technology, all the technology we use every day, and while I'm not one to complain about it, I think we have kind of forgotten some tricks and formulas, and a bit of knowledge has gotten lost over the years because it's easier to rely on machines and computers to make these calculations for us. So I've dug out a few. Some of them I've known for a couple of years, and some of them I found when I was preparing this list of formulas. And most of these are, just working things out from your surroundings, or just from some numbers or figures you already have, changing them into something else, or even using your body, the sun, and even insects to estimate things about the world around you. The first calculation we're starting off with is probably not very good practice of mine, but I haven't had a chance to try it, and it's something I haven't even really been able to verify. But I found it in a lot of different places on the internet and on a lot of science pages, so I don't know, it seems to be widely believed. And this is the formula for calculating the temperature without a thermometer, but you do need a cricket. And this is because apparently crickets sing or chirp more frequently the higher the temperature is, to a certain point, I presume. So most species of crickets chirp faster the higher the temperature is. For example, 62 chirps a minute at 13 degrees. Each species has its own rate, but that seems to be quite a common rate. And apparently the relationship between temperature and the rate of chirping is known as Dolbear's law. According to this law, counting the number of chirps in 14 seconds that is produced by the snowy tree cricket, which is common in the United States, then adding 40 to that number will get you the temperature in Fahrenheit. So the number of cricket chirps in 14 seconds plus 40 will give you the temperature in Fahrenheit. If anyone has ever tried that, you can let me know. If you want it in Celsius, it's a little bit more complicated, but not that difficult. Count the number of chirps in 25 seconds, divide by 3, and then add 4, and then you will have the temperature in Celsius. Here it is, Dolbear's law, number of chirps by the cricket in 14 seconds plus 40 gives you your temperature in Fahrenheit. For example, 28 chirps in 14 seconds plus 40 means it's 68 degrees Fahrenheit. Number of chirps in 25 seconds divided by 3 plus 4 gives you your temperature in Celsius. Example, 45 chirps in 25 seconds divided by 3 is 15 plus 4 means it's 19 degrees Celsius outside. Of course, there is a drawback to this method, as well as the fact that maybe you'll be listening to the wrong species of cricket. You have to hear just one cricket, how many chirps they're making, which I think is pretty difficult in the countryside unless you are right beside one. Keeping with the theme of temperature, I think it's a good idea to know the formulas of converting Fahrenheit to Celsius and Celsius to Fahrenheit. I always get really confused when I hear people talking about Fahrenheit because I always think in Celsius. So the formula for converting Fahrenheit to Celsius is Fahrenheit minus 32 divided by 9 multiplied by 5. And then to get the other way back from Celsius to Fahrenheit, you just do the opposite. Divide by 5, multiply by 9, and add 32. It's pretty straightforward. There are other ways to do it as well, but they involve multiplying by fractions or decimal numbers, and I think it's always easier to work with whole numbers as much as possible when you're involved in mental arithmetic. Then of course we do have another way, to tell the temperature, another scale, and that is the Kelvin scale, which goes all the way down to absolute zero. That's where it starts. There are no minus numbers in the Kelvin scale. To convert this into Celsius, it's not very complicated. You just have to make a simple equation. When you have your value in Celsius of the temperature, take away 273.15. And then you've got your number in Kelvin. Fahrenheit to Celsius. So let's check it out with the temperature we know already, usually in both scales, which is body temperature, 98.6 degrees Fahrenheit. So here we know the formula. Take away 32, which is 66.6, divided by 9, and then multiply by 5, and you get 37 degrees Celsius. In Celsius to Fahrenheit, we just do the exact opposite. Divide by 5, multiply by 9, and then finally add 32. So let's double check this with a value that we know is the same on both scales, minus 40. So minus 40 divided by 5 is minus 8. Multiply by 9, minus 72, plus 32 is minus 40. So there you go. Converting to and from Kelvin is pretty simple. You just either add or subtract 273.15 because that is the value of absolute zero. That is where the Kelvin scale starts. So to get to Celsius, just take away that number from the value in Kelvin. For example, 300 Kelvin minus 273.15 is 26.85 degrees Celsius. And we do the opposite to get the value in Kelvin. 0 degrees Celsius plus 273.15 gets you 273.15 Kelvin. I remember once a couple of years ago hearing a joke. Did you hear about the man who reached absolute zero? And the answer was he was okay, as in 0K. Okay, so let's move on to distance. First of all, the distance of the horizon, how to tell how far the horizon is from the point you are at if you know the height of your eye level. So there are different ways, there are different formulas, but we'll start with my favorite way to get it first, and that is the square root of the height of your eye in feet multiplied by 1.17, and that will give you the distance to the horizon in nautical miles. You can of course convert nautical miles into kilometers. That's about 1.9 kilometers in every nautical mile, or you could use a different formula, which is the distance to the horizon is 3.57 multiplied by the square root of your height, of your eye level above sea level. And what about if you don't want to know how far away the horizon is, but how far away something is on the other side? So maybe you can't see the base of the object, but you can see the top. Then you would just need to do this calculation twice, but you also have to know the height of the object you're looking at. For distance to the horizon, let's start off with my favorite formula. That is the square root of your height above sea level, ground level in feet, multiplied by 1.17. So let's imagine you are maybe 6 foot, you're on a boat, which adds another 10 feet above sea level. So the total height of your eyes is 16 feet. You want to know how far away you can see. So square root of 16 is 4, multiplied by 1.17 is 4.68. This gives you the answer in nautical miles, 4.68 nautical miles. A nautical mile is about 1.85 kilometers. The other way to do it, if you want to get the answer directly in kilometers, is this equation here. D for distance in kilometers equals 3.57 multiplied by the square root of the height of your eyes above the sea in meters. So let's imagine maybe your height is 4 meters if you're on a little hill or another boat. That's 3.57 by 2, which means the horizon is 7.14 kilometers away. What if you can see something over the horizon? Maybe you can see the top of it, you know how tall it is or how tall it should be, but you can't see the bottom. You can figure out how far away it is by using these equations twice. Figure out your distance to the horizon and the distance of the top of the object to the horizon, and then add these two values together. So we can imagine maybe my eyes are 25 feet above sea level, and the top of this tower here is 16 feet above sea level. So filling in the values to our formula, we get 5.85 plus 4.68, which is 10.53. So I use the first formula, so that gives me the answer in nautical miles. However, when calculating the horizon, we have to keep in mind that the Earth is not a perfect sphere, and also, more importantly, a person will typically see a little bit further along the Earth's surface, curved surface, than the answer that we get from the calculation, and that is because of refraction error. So if the ground or water or surface is colder than the air above it, a cold, dense layer of air forms close to the surface, and this causes light to refract downward as it travels, and in a way to kind of go around the curvature of the Earth. We see the opposite happening when the ground is hotter than the air above it, for example, mirages in deserts. But if you want to compensate for refraction, apparently surveyors measuring distances longer than 300 feet subtract 14%, and also ensure lines of sight are at least 5 feet from the ground. One more distance calculation, and that is to tell how far away something is from you if you know more or less its size, its length. You can do this by standing outside, looking at the object that you want to know how far you are away from. Hold out your arm directly in front of you with your thumb straight up, like this. Now, this is based on distances within our body related to the distances outside. So the space between your eyes is generally about 2 inches. The space between your eyes and the tip of your thumb is generally about 20 inches. So we get 10 times the distance from thumb to eyes as the distance between each eye. So using this knowledge, when we look at the object in the distance and close one eye and then close the other eye and see how far the two images of your thumb move. So for example, if you are looking at a car in the distance, you want to know how far, a parked car, you want to know how far away it is. If your thumb jumps the distance, the entire distance of that car when you move your eyes, when you use different eyes, and if you know that the car is generally around 5 meters, 4 meters for a small car, then you can calculate that the car is 5 meters, so the space between the thumbs, multiplied by 10, 50 meters away. Okay, so here's a diagram of how it works. If you're standing there, looking at your thumb, looking at the car in the distance, you know the car is most likely about 5 meters. So if your thumb, when you close each eye, jumps the whole length of the car from the beginning to the end, then you can multiply the length that your thumb jumps, in other words 5 meters, by 10 to get the distance you are away from the car. If your thumb only jumps like half the car, you can say your thumb is jumping 2.5 meters at that distance, and then you would multiply that by 10, so it would only be 25 meters away. And here's how it works. If you have a ratio of 1 to 10 between the distance of your eyes and the distance from your eyes to your thumb, and then both triangles, the car being at the other end of the other triangle, have the same angle, then you can use the length that your thumb jumps to calculate the distance. This one I learned a few years ago and I thought it was fantastic. I thought it was a really exciting discovery and I'm still pretty impressed with it, and that is how to tell the time by looking at the sun. There are a couple of things you need to know though. You need to know what time the sun rises at or what time it sets at to properly complete your calculation. So what you need to do is look at the sun has to be shining in the sky, and reach out your hand, a spread hand like this, and put your baby finger where the sun is. So if the sun is here, put it here. And placing the top of your baby finger where your thumb last fell, you repeat the action until your hand reaches the horizon. I think we're going to have to go to the paper on this one. Telling the time with the sun and with your hands. Obviously this works if you can see where the sun is in the sky, and hopefully you will know what time the sun sets at or what time it rises if you're working the other way at the other end of the day. So let's first imagine we can see the horizon here and the sun here in the sky. So what you do is you hold out your hand, put your little finger just touching the sun, mark the point where your thumb falls, and then repeat the same movement again. Follow on with your baby finger to your thumb and your baby finger to your thumb until you reach the horizon. And then count the number of hands while you're doing this. Here we have nearly 4 hands. So this means there are nearly 4 hours left until sunset. I really like this way because I find I can get it to within 15 minutes of the correct time, and I've tried it at different times of the year and it always gives me the right answer. Another option, which I haven't actually tried out myself, is some people count how many fingers there are between the horizon and the sun to find out how long it is until sunset. I don't know if this only works in the evening or if it works all during the day, but apparently each horizontal finger stands for 15 minutes. If you have very large or very small hands, you might want to calibrate your instruments, that is your fingers, to a clock before relying on them. For example, some people might have fingers that represent 20 minutes or 13 minutes or 12 or 10 minutes instead of 15. And finally, for the last formula, finishing with one that everyone probably knows already, and that is to tell how far away a thunderstorm is, or at least the part of the thunderstorm that you have listened to in that moment, because of course they can be very big. We do this by counting the seconds between the flash of lightning and the sound of the thunder. Sound travels slower than light through air, and generally we count 3 seconds to mean 1 kilometer. The speed of sound can change depending on the temperature as well. So in dry air at 0 degrees Celsius or 32 Fahrenheit, the speed of sound is 331.2 meters per second. And if the temperature were 20 degrees Celsius or 68 Fahrenheit, then the speed of sound is 343 per second. So 330 is kind of in the middle. But I guess you don't need to know the distance of lightning and thunder down to the meter. Hope you've enjoyed these calculations and formulas. I'm sure there are many more which I am not yet aware of, and I think it's fun to know things like this, even if we never need to use them, but it's always best to be prepared because we never know when the next solar storm is coming. See you soon.